Hi everyone. So we've been studying the dot product, and the key thing about the dot product is that it allows us to compute geometric information, such as things like distance and angles. And this can be useful in a lot of ways. In particular, we have these nice orthogonal projection formulas, and we have a way of finding best approximate solutions in cases where there is no exact solution to an equation. But it's worth remembering that the dot product is only defined for vectors in Rn. So what if you have a linear equation in some other vector space, like a function space? What can we do to get best approximate solutions in those cases? So this leads us to the concept of an inner product. An inner product on a vector space V is an operation that has properties that are similar to a dot product. So let's be more precise. So first of all, what kind of an operation is it? Well, just like the dot product takes two vectors and then their dot product is a number, if you take two elements of the vector space, then their inner product should be a real number. And just make sure that you observe the notation here, that the inner product is denoted with these angled brackets with u and v inside. So what else? Well, basically you want to be able to do calculations with inner products that are similar to calculations that we do with the dot products. So one thing you would want for that is distributivity and scalar compatibility. So for example, if you have the inner product of u with v plus w, then that should distribute to give you the inner product of u with v plus the inner product of u with w. And similarly, you would want to be able to pull scalars out of an inner product. Another thing that you would ask for is symmetry, that the inner product of u with v is equal to the inner product of v with u, just like with the dot product. And then there's one more thing, and it might seem a little bit weird at first. It's called positive definiteness. And what it says is that if you have a non-zero element of v, and you take the inner product with itself, you should get a positive number. And the reason for this is that it allows us to get a good notion of length of a vector. Remember that in Rn we have this equation that the length of a vector is equal to the square root of the dot product of that vector with itself. In a general vector space, there's no pre-existing concept of length of a vector. But if there's an inner product, then we can define the length of a vector to be the square root of the inner product with itself. And then the positive definite requirement guarantees that this is well defined in the sense that we don't have a negative number under the square root, so we don't have an imaginary length. And it also guarantees that the only vector with zero length is the zero vector. And so all of these conditions together give you the definition of an inner product on a vector space. Now, you probably still feel like you don't understand what an inner product is, and that's totally normal. That's because this is an axiomatic definition, just like when we were defining vector spaces with axioms. And so what that means is that there isn't one specific operation that is the inner product. Anything that satisfies these axioms counts as an inner product, and there can be lots of different things that satisfy the axioms. And so in principle, you could study inner products using these axioms in the same way that we studied vector spaces in terms of the axioms. You can prove things about inner product and so on. But because we're short on time in this class, I'm going to focus on one specific class of inner products that's particularly useful and interesting. So the example we're going to focus on is an inner product on a space of functions. And in particular, it's the space of continuous functions on an interval AB. And we'll use C of AB to denote that space of functions. So we want to define an inner product on this space, which means that if you have two functions that are continuous functions on this interval, then we want to be able to produce a number out of those two functions. And one way to do that is to multiply the two functions together and then integrate from A to B. That will give you a number. And I think it's a good exercise for you to check that this definition of an inner product actually satisfies those properties that we discussed earlier. Distributivity, that you can pull out scalars, symmetry, positive definiteness. All of those things are true, so this does actually satisfy the definition of an inner product. And actually, it's worth pointing out that this is basically a continuous version of the dot product. With the dot product, you multiply the corresponding numbers in the vectors together, and then you add everything up, right? In this case, you're multiplying the corresponding numbers in the functions together, and then you integrate them, which is the continuous version of adding the numbers together. So hopefully you're willing to believe that this inner product would lead to a good notion of distance for functions on the interval AB. Okay, so now the big question is, what can we do with this? Well, the key point is that everything that we did with dot products, the concept of orthogonality, orthogonal projection formulas, etc., all of that stuff carries over directly into this setting where we use the inner product instead of the dot product. So here is a good example to get started. Suppose we wanted to find the line through the origin that best approximates the function y equals sine of x on the interval from -1 to 1. So just to rephrase this question in another way, we want to find a number m such that m times x is closest to sine of x on the interval from -1 to 1. And I put the word closest in quotes because there can be different notions of what it means for functions to be close to each other. But in this context, we're using the notion of distance that comes from this inner product. So anyway, how do we solve this problem? Well, I think it might help to think about how you would solve a similar problem with vectors instead of functions. So let's say I gave you two vectors, u and v, and I asked you to find the constant m such that m times u is closest to v. You would solve that problem by orthogonally projecting v onto u. And so in this case, we're going to do exactly the same thing. We're going to orthogonally project sine of x onto x. And actually, even though this picture isn't literally accurate, it provides a pretty good sketch of what's going on here. The set of all functions of the form mx forms a line in the space of functions. It's actually a one-dimensional subspace. And then we've got sine of x, which isn't on that subspace, and we're trying to find the point on that subspace that is closest to sine of x, and we obtain that by orthogonally projecting sine of x onto that subspace. And so then to do this, we use the orthogonal projection formula. And it's exactly the same formula, but with functions in place of vectors and the inner product in place of the dot product. But it's exactly the same formula. And so now all we need to do is calculate it. So the first thing would be to rewrite the inner products as integrals. And so on top, you have the integral from -1 to 1 of x times sine of x dx. And in the bottom, you have the integral from -1 to 1 of x squared dx. Note that the bounds for the integral comes from the fact that we're trying to approximate the function on the interval from -1 to 1. All right, now this isn't a calculus class, and I'm not going to expect you to do these integrals by hand, so please use a computer or a calculator to do these integrals. And so what I got was that the integral in the numerator was approximately 0.6, and then the integral in the denominator is 2/3. And so that's about 0.9x, and that's the answer. The line through the origin that best approximates y equals sine x on the interval from -1 to 1 is approximately y equals 0.9x. And just so you know, the word approximately there is used because I rounded to 0.9. Now, it's worth thinking a little bit about what does it mean that we got 0.9x as the best approximation to sine of x. And maybe a good way to answer that is to compare with another reasonable approximation, which is the tangent line. At the origin, sine of x has a slope of 1, and so its tangent line there is just y equals x. Now, in general, a tangent line is a really good approximation when you zoom in really close to that point of tangency. And so in this case, the tangent line y equals x is a really good approximation when you zoom in really close to the origin. But as you move away from the origin, the tangent line becomes less good of an approximation. And in particular, you can see that the tangent line is an overestimate for positive values of x and an underestimate for negative values of x. And so if you lower that slope a little bit, then you can get something that's a better estimate over the entire interval. And that's exactly what we found when we did this calculation. And so hopefully that gives you an idea of what we mean when we talk about a best approximation. It's not just an approximation near a single point, but it's supposed to be a good approximation throughout the entire interval. Okay, so let's look at another example. Suppose we want to find the line that best approximates e to the x on the interval from -1 to 1. This is a little bit different from the examples we just did because we're not restricting ourselves to lines through the origin anymore. So the space of lines isn't just one-dimensional, it's two-dimensional. So maybe it's worth pointing out that the stuff that we did with normal equations when we were solving for best approximations before, that's a lot more complicated actually in the case of inner products. So we're not going to do that. So for us, the only tool that we have at our disposal is orthogonal projection formulas. So when you have 2 degrees of freedom, it's important that you find an orthogonal basis for that space. But in this case, we're lucky because the standard basis elements, 1 and x, are actually orthogonal on the interval from -1 to 1. And you can see this just by doing the calculation of the inner product. When you take the inner product of 1 with x, that's the integral from -1 to 1 of 1 times x, and when you calculate that integral, you get 0. And so that's great. That means that we can use the orthogonal projection formula. And so just to be clear about what we're doing here, the space of all lines is P1. And so what we're calculating here is the orthogonal projection of e to the x onto P1. And so this is the formula for that orthogonal projection, using the fact that 1 and x is an orthogonal basis for P1. And so now it's just a matter of calculating. So we can rewrite all of these inner products in terms of integrals. And then if you use a computer to calculate those integrals, what you get is about 1.2 plus 1.1 times x. And so that's the formula for the line that best approximates e to the x. And I encourage you to graph e to the x and graph 1.2 plus 1.1x, and you'll see that it actually is a pretty good approximation on the interval between -1 and 1. Okay, so now let's suppose that we wanted to find an even better approximation by finding a parabola instead of a straight line that approximates e to the x. So you might think that it's just as simple as doing what we did in the previous example, but adding an x squared term. But the problem with that is that x squared is not orthogonal to 1. So you can't use the orthogonal projection formulas with 1, x, and x squared because they're not orthogonal. But it turns out that if you use 3x squared minus 1, that does form an orthogonal set with 1 and x. And you're probably wondering, where did I get 3x squared minus 1 from? And my response is, don't worry about that right now. There is a process for finding orthogonal sets, which is called the Gram-Schmidt process, but we didn't have time to talk about that in this class. So anytime you're going to need an orthogonal set, I will give it to you. But before we proceed, I should probably ask you to think about how you observe that these things are orthogonal. And to do that, you need to take inner products of all of them with each other. So for example, we'll do the inner product of 1 with x. That's going to be the integral from -1 to 1 of 1 times x dx. And when you calculate that integral, you'll get 0. Similarly, the inner product of 1 with 3x squared minus 1 is the integral from -1 to 1 of 1 times 3x squared minus 1. And when you calculate that integral, you'll get 0. And then finally, you need to look at the inner product of x with 3x squared minus 1. And when you compute that integral, you also get 0. And so these three calculations together tell us that 1x and 3x squared minus 1 are orthogonal. And now that we know they're orthogonal, that means that we can use the orthogonal projection formula to project e to the x. Now, the first two terms in this formula are exactly the same things that we calculated in the previous example, where we got 1.2 plus 1.1x. So we just need to calculate this last term and add it in. So to do that, just like with the other terms, the first thing to do would be to rewrite the inner products as integrals, and then we can plug those integrals into a computer and calculate. And then when you do those calculations, what you end up with is 0.2, rounded to 1 decimal point. And so then you can put that number in and simplify the expression. And what you get is 0.6x squared plus 1.1x plus 1. And so that's the equation of the parabola that best approximates e to the x on the interval from -1 to 1. And again, I recommend that you graph this and observe that it does do a pretty good job on that interval. I will point out that I've been pretty cavalier about rounding the numbers to 1 decimal point, and if you included more decimal points of accuracy, then you would get a better answer. So anyway, this is just a quick introduction to inner products on function spaces, but I wanted you to see it because I think it's a pretty cool idea, and it has a lot of important applications. For example, this kind of inner product plays an important role in quantum mechanics, and if you look through a book on quantum mechanics, you'll see a lot of orthogonal projection formulas just like this. And another place where this kind of inner product appears is in Fourier series. So this is something you probably haven't studied it before, but maybe you've just heard that word. Basically, what a Fourier series does is that it takes a wave, like a sound wave, and it decomposes it into its constituent frequencies. So for example, you're listening to my voice right now coming out of a computer. How is that happening? The algorithms that encode and decode sound waves into data use Fourier series and a more fancy version of Fourier series that's called the Fourier transform. Now, back in the day when I was first learning about Fourier series, I didn't learn it this way. There was just a long list of formulas that I had to memorize. And I remember thinking, like, how on earth can I memorize all this? It's so complicated. But now I know that all those formulas are actually just orthogonal projection formulas. And knowing that makes it feel a lot less overwhelming to me. I don't have to memorize a long list of formulas. There's just the orthogonal projection formula.